Today we will continue our discussion on tree, a new feature of tree. So far what we discussed, that is the basic features of the tree, how many trees uh, can be there, the different forms, binary search, binary search tree, B tree, AVL tree, how to make an unbalanced tree to a balanced tree, different traversals technique in order, pre-order, post-order, how to form a tree from in order and pre-order traversal, pre-order sequence of the nodes, how we can form a tree. This we have discussed earlier. And minimal spanning tree, right? We have discussed. Today we will discuss a new feature of tree, that is heap. There is a sorting technique called a heap sort. So using this technique, we can also arrange a collection of data in a particular manner, ascending order or descending order, using this technique. So this is one of the techniques of different sorting techniques, heap sort we call it. So today we will discuss uh, about heap. Okay. So let me present. The screen is visible to all of you.
Yes, sir.
Yes, sir.
So the heap data structure. Heap is a special case of balanced binary tree. You know what is a balanced binary tree? Balanced binary tree we call when, that is, each and every node of a binary tree gets
integer type
the
of type.
weightage ranging
Also,
from -1
there are two
to
dimensional
+1.
array of
It
different.
-1,
All of you can
it may
find
be
and declare macro.
0, or it may be
So,
+1.
but scan
All
that
this we
Jyotish
have discussed
character
in the earlier classes.
be
So heap is a
elements.
special case of
The
balanced
record
binary
have
tree
given
data
a name.
structure
Fields
where
are called
the root
hooks
node
type to
key is
handle the structure.
compared with its children
Tools here
and
will be
arranged accordingly.
printf,
If
percent
alpha
%d and book
has
id. These are
child
the
node
string.
beta, the alpha has a child node beta, means beta node is a child of alpha, then this will be the generic formula. Key, key means value of alpha node. Okay, key alpha must be always greater than, equal to key b. As the value of parent is greater than that of child, this property generates maximum heap. Mainly there are two kinds of heap tree, maximum heap and mean heap. In maximum heap, always the parent nodes will be having the greater values, and mean heap, it will be just opposite. But the value of the root node is less than or equal to either of its children. Okay, got it? Always the parent node, value of the parent node will be greater than the value of its child nodes in case of max heap, and in case of mean heap, always the parent node will be having the less or equal value of its children. So here, this is an example of mean heap. You can see always the root node or the root node always having
Okay. So
the
all of you
less
can
value than all
see
of
me, now can
its
watch
the
me
child
on
nodes.
the
Okay.
mode.
Here also you can see maximum
Hello.
max tree
The
always
discussion,
the root node
and
will be
then
having
we
the
need
greater
to
value than
access
its
member of the
child
structure,
nodes.
and
Okay.
again the variable at runtime
So
PC.
as we will
Full
forming
we have got
with an
that is the
example
first steering.
max
Let me
for
run
heap,
this one.
it will
Should
be more
all of you
clear.
is at the time of
Both trees are
printing this.
constructed using the same
Anyways,
input
now
and order
let's
of arrival. So massive construction, definitely what we
study.
do in a data
We want to
structure,
do, we are
always we
going now to do the same thing with the
generate
function as I
a
told you.
device and
Yes,
algorithm. There
and
must be
the
a sequence
as
of logic.
usual I have
So maintaining that logic, we solve a particular problem in data structure. So maximum this is the 5 steps of algorithm are there. Create a new node at the end of it. First, whenever we are going to insert a new node, we have to put at the end of heap. At the end of heap means we will insert the new node in such a way that the balancing of the tree doesn't get disturbed. We have to maintain the balance. That's why heap first the definition we mentioned that heap is a special case of balanced binary tree. Why it's a special case? Because it is not a general case where that we cannot give a guarantee that this root node will always be having the greater value of the maximum value or minimum value for the mean heap. That's why it is a special case. Okay. Now, after we insert a new node at the end of heap, assign new value to the node. Means each and every node must be having a value with it. Compare the value of this child node with this parent. If the value of parent is less than, if the value of the parent is less than the child, then swap it, right? Because always the child node will be having the will be placed at the top of the heap. That's why it will be swapped. Repeat steps 3 and 4 until the heap property holds. Now until and unless we try to analyze it with an example, it will not be clear. So it is an example of max heap algorithm, and in mean heap construction we expect the value of parent node less than that of the child node. Let's understand the heap construction by an animated example. So next, there is an animation we call it maximum construction. All of you just follow the animation. Here, when we insert a new node at the end, it's a maximum heap construction. See, if the just could you see how this 14, how all of the nodes when we are trying to place it, maintaining the max heap, you can see this the child node is gradually getting up according to its value. But in the case of maxing, always the node which will be the maximum node will be at the top of the list. Okay. Just try to let me try some just if I start it from. See, when we insert a 14 here, after in this case that 14, when we insert a new node, first that new node will be having the place of the top, and after that, that 14, that value, that node is getting shifted gradually according to its values. 14 is less than 13, so 14 will be here. Now 14 will be less than 26, that's why 14 will be here. After that, got it? Hello.
Yes, sir.
You just follow the animation. Who's there? Someone is trying. So this is the map sheet. Input is 35, 33, 42, 10, 14 and 8. First when 35, starting with 35, then is compared to 33. Okay, it's fine. Then 42 will be the greater the greater value. That's why 42 will be raising up this way. Again, I will repeat again when it will be started from the beginning. Let it start again. Again, just see. It's over, I think. 35, fine. 33 is less than, so it's fine. 42, but 42 will be at the top. Then 10 is fine. 14 compared with it, 14 is fine. 19 is fine. 27 is fine. Now 44. Now 44 will be placed at the top. Gradually it will be raising up. Okay. So the main thing is that whenever we will be inserting a new node, we have to compare the new node with its root node, not the parent node, root node. Root node means the root which will be placed at the top. So it will be compared with the root node always. 19 is fine. 27 is fine. 44, 10, 33. So it will be gradually raising up. Got it? Got it? So
Yes, sir.
in this way, if we maintain right from the beginning, so always we will be having a balanced binary tree, and in case of MAXIP, the greatest value, maximum value will be at the top. This way we have to arrange the tree. Okay, so you have to maintain this one only. Got it? I think if you follow the lecture again, you will get to know. Okay, later on if you have any confusion, it's very easy. Fine. So mean heap is just opposite of this. Now deletion will be what? Just and that maintaining that logic. Remove the root node first. If we remove the root node, definitely that place will be occupied by some other child nodes. So move the last element of the last level to the root. What is happening? You just follow. Maximum deletion. So if we want to delete particular node, we have to delete 44. Now when 44 is deleted, last node was 14, so 14 has been placed here. Then 14 will be gradually coming down to get its proper position. This was a tree. This was a tree, heap tree. So 14, we have deleted the 44. After deletion 44, the 14 was the last node. So 14 got the place at the root, but it should not be placed over there because it is violating. If the 14 is placed here permanently, it will violate the rule of the heap. That's why 14 should come down to its proper position. Got it? Very easy. See, 14 has been replaced here, then 42, then 14 compare 33, 14 come here, 14, 26, no, 14 has come here, but then 42, it will violate. Ultimately, for this will be our final version of the tree after we delete our a particular node from the heap. So the algorithm is very easy. The algorithm: remove the root node, move the last element of the last label to root. Okay, move that last element. Compare the value of this child node with its parent. If the value of parent is less than the child, then swap it, because the it should the child node should be having the less value. That's why. Repeat steps 3 and 4 until the heap property holds. Very easy. Okay, got it. So this is a special type of balanced binary tree where we have to maintain this one. Got it? Hello.
Yes, sir.
For the deletion, what we did after we delete 44, 14 got placed here. But 14 should not be there. It will violate the rule of the massive. So 14 should come down. Where you need to know which position. You compare the two childs. 42 is greater than 35. So 42 should come. Should be swapped with the 14. So when we swap it, 14 will come here. Now 14, compare the 14 with 33 and 31. So 33 is the greater. So 33 will come here and 14 will come here. Now compare this 14 with 10 and 26. 26 is greater. So 26 will come here and 14 will come here after we delete this one. Okay. Now that eventually you can see that 14 has got the place from here to here, right? It has moved from here to here through this route. Got it? Through this path. Understood? This is
Yes. Yes, sir.
deletion of heap. Deletion of a node from a heap. It's very easy. Now there is an short, very small topic. I think you have, all of you have used this recursion, this technique in C, right? Have you heard the term recursion, recursive function? Hello. When you studied the function in your
No, sir.
in
Yes.
CS 201 subject, so you started this one, but probably you have not analyzed it in that way. So you have to understand this, that we know that in any recursion means the function will call itself iteratively until and unless it gets a termination condition. If it doesn't get any termination condition, it will go on working indefinitely. So it will have an infinite loop. So ultimately the program will have a runtime error, right? If a function always calls itself, and if we can't stop that calling at times, so it will have an infinite loop. So we have to stop this. So we have to put a condition where this calling will be stopped, right? So that is a condition, mandatory condition of recursion function, number one. And number two, there will be a base condition. Base condition means, this is called the base condition. Actually, you can see that the basic criteria, that there must be at least one basic criteria or condition such that when this condition is met, the function stops calling itself recursively. This is what I said, that at times it must be stopped. So this is the best criteria. And progressive approach, the recursive calls should progress in such a way that each time a recursive call is made, it comes closer to the base criteria. So always the condition of calling will be such that it meets the, it tends to meet the base criteria. Got it? Let's say if I try to just a minute. If I try to, if I try to factor, if I try to find out the factor of a, well, let's say factor 5, right? So what will be the factorial of 5? 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. Right, isn't it?
Yes, sir.
We are calling what? We are multiplying with the current value which is the previous one, right? We got 5, then again we have to reduce the value by 1, then that it will be 4, comes out 4, and 4 will be multiplied by its previous result of the previous function, previous version, right? So multiplied by 5, then 4, then 3, then 2. So it is reducing, it is coming down to its base criteria, where we have to put a condition that if how many how long it will be continued, the calling will be continued, so long it will have the value greater than 1, greater than equal 1. If it returns 0, it will be stopped, isn't it? 5, 4, 3, 2, 1. So the 1 will be the base condition, right? After that, again, if I try to deduct 1 minus 1, that will be 0. So if I take that value into consideration, the calculation will be wrong, because eventually it will be multiplied by 0. So we'll get the 0. Factorial of 5 will return 0, isn't it? So the base condition is 1. So you can see that each time of calling, the calling pattern is tending towards this, is coming towards its base condition, that is that the value must be eventually greater than equal to 1, right? So this is what is mentioned here. Yeah. This the recursive call should progress in such a way that each time recursive call is made, it comes closer to the base criteria, right? So with an example, you can see this is a function in value. If value less than 1 return, so this is the base criteria, right? When the value will be less than 1 means is 0, right? It will return, means we will not call the function anymore again. Okay. And each time you are calling the same function with the -1, it's just a function which calculates the factorial of a value. Got it? Fine.
Yes.
And there is another hidden criteria which is not mentioned here. You can get it in the question at the time of campus interview. So apart from these two criteria, is there any criteria which must be maintained by the system? There is one criteria, but generally it doesn't occur. See, you can see that whenever we are calling this function repeatedly, the first time 5, if I find out the factorial of 5, so first 5 will be checked, not it is not less than 1, it's greater than 1. So again, the value is 5, 5 minus 1, the function is again called, right? 5 minus 1, 4, then 4 minus 1, 3, 3 minus 1, 2, 2 minus 1, 1, then 1 minus 1, 0, but it will be stopped here. It is no, less than, not less than 1, right? It is less than 1, so it will be returned. You can see that each time the value will not be printed, because value will be printed when that recursive calling will be stopped, then value will be printed. Okay, means ultimately 5 multiplied 4, 3, 2, 1, 120, isn't it? Factorial of 5 is 120, na? Right?
Okay. Okay.
আলটিমেটলি 120টা লেখা হবে, প্রত্যেকবার কিন্তু 5 4 3 2 1 লেখা হচ্ছে না, এখানে আমরা ক্যালকুলেট করছি, এখানে আমরা ফাংশনটা দিয়ে ক্যালকুলেট করছি এখানে। হ্যাঁ, এখানে বুঝতে পারছিস? তাহলে এখানে আমার কোশ্চেনটা হচ্ছে we have to store the intermediate result in somewhere, ना,
जो
so that we can get it in
आवाज
case
करते हैं,
of
साउंड प्रोड्यूस करते हैं, ठीक है,
in
साउंड
case
वर्ड है
of
साउंड से।
factorial,
तो देखो ये सारी इक्विपमेंट है।
in case of finding out the factorial, we are multiplying Okay. Actually, this is not an example of factorial. It is just example of the printing the values. I think factorial is not here. Factorial means we have to multiply this one with this. Understood? So in it will be value star function value minus one. Got it? Value multiplied by value function this. So my point is this, that somewhere the intermediate result 5, 4, 3, 2, 1 it will be stored somewhere, na? So actually the recursive function uses a stack. But what stack? It is not our stack. It is a system stack. Means in CPU there are some registers, no? In some teeny memory locations. So in these registers, the intermediate results are getting stored. Now, if the system doesn't support that memory, that internal memory register, right? If it is runs out of memory, then the program will terminate abruptly. So this is another hidden criteria. So the system must support the uh, the right, so that the intermediate result can be stored sufficiently by the system, right? So this is another condition. Anyways, a function calls another function which
Q,
in
that is
turn
adding an
calls
element.
it again. This is an example. Same thing. Function 2 is
Element of
calling
the queue, and
this
real
hello 1
after the
function 2, right? Function 2 is calling again function. There is another version we can say that function 1 is calling function 2. So after that function 2 is calling again this function 1. So this may be another form of recursion. So properties we have discussed. Implementation. Many programming language implement recursion by means of stack, system stack. Generally, whenever a function calls another function or itself as callee, the caller function transfers the execution control of the callee. The transfer process may also involve some data to be passed from the caller to the callee. Oh, we have discussed all this. This implies the caller function has to suspend its execution temporarily and resume later when the execution control returns to the callee function. See, this is a stack system stack. That what I was telling you, right? So if you want to uh, find out the factorial of n, so factorial of this is the first iteration when we are trying to find out the factorial of n. Then value of the n will be subtracted by 1. So the next version will be the second iteration will be factorial of n minus 1, then n minus 2. Gradually it will come to 1, right? And so when we are calling these functions, so that what you are telling, or I was telling you, that it must be stored in some internal place in the memory, na? Internal, that is a register, what we are calling about system stack. So the function n means 5. Here 5 will be placed in the stack. Then 4, then 3, then 2, then 1. Ultimately, multiplying as a whole, we will get the result. So this intermediate result must be stored in the system stack. This is the pictorial representation of that point. So time complexity is order of n, space complexity. Some extra space is required for module to execute. All these very easy. So this was a short topic on recursion. We will show you some recursion example in some practical implementation of recursion, uh, writing some code later on. Okay. So this is
Okay, sir.
today's class. I will give you the material. So it will not be included in your SWOT 2 internal test. Okay. So don't get worried about this. So you can see that you don't have to write any code for this. You don't have to understand. But if you
So
get interested, then I will
as
give you
we
the code
implemented
for how we
the
can make a heap, how we can
step,
create a heap, how we can delete a heap. All these programs are available, but it is not in your syllabus. So don't get worried. You just try to understand the theoretical aspect of this first. Okay. So let's
Okay, sir.
this class. See you in the. I mean, tomorrow we have a class again, na?
No, sir.
Tomorrow it's not. Then okay, I will search the routine. Okay, I'll inform you.
Okay.
Mm.
Thank you, sir.
Okay.